All right, so I'm going to do practice quiz 3 in preparation for quiz 5 as part of this virtual lecture 8 series. So in this problem, the solutions are of course already up on a PDF, but I'm going to go through it and add kind of some new content that makes this solution a lot easier to solve. In this problem, we have two students that hung this bar that weighs 20 kilograms, and it says it's uniform, which just means that there's no change, like it's not denser at one end or the other. And they hang it from the ceiling by one end, by this rope, and one of them stands on it, and the other one pushes up on the other side. And that the system is in static equilibrium. So static equilibrium means that our F net and our tau net are both 0, right? There's no net force or net torque causing it to have a change in momentum or angular momentum. And not just no change, but they stay at 0. So everything is stationary. So these two equations are super powerful. The tau net equals 0 means that tau into the page and tau out, both directions of rotation, are equal and opposite, and F net equals 0 has an x and a y component, and in both of those directions, all the forces have to cancel. Okay, so question A asks us to find Chelsea's mass. So Chelsea is the student standing on top of the bar. And we have to draw an extended force diagram as part of our explanation. So why don't we start there, because that is a very helpful problem-solving tool. So let's add the forces. We have the tension from this rope, which is pointing up. The force is pulling that up. We have the force from Chelsea standing on the bar, which is pointing down. We'll call that FC, and we'll call this tension. And then we also have the force from Anthony pushing up at the end of the bar. We'll call that FA. And then finally, I have the gravity of the bar itself, which acts at the center of mass. So that's something we'll have to get used to, is gravity acts at the center of mass of whatever object we are looking at. So since this bar is 1 meter long, the center of gravity is halfway in between the two ends, or 0.5 meters from either end. So this FG is situated exactly halfway between the two endpoints. And each one of these forces has some torque. So that's the point of us drawing this extended force diagram, is that we can identify the torques that each one produces. But before we do that, we have to identify the center of rotation, or the axis of rotation, or the pivot point, or whatever we want to call it. But where is the pivot point? And a key new topic in a problem like this is that in static equilibrium, we are free to choose that point wherever we want. Since nothing is rotating or moving, then all of the forces and all of the torques are going to balance out no matter where our reference point is. So I guess for forces, the reference point doesn't matter, but for torques, we know that torque is equal to some F perpendicular times R, or some R perpendicular times F. And so this R matters. The distance between the pivot point and the force is really important. So if I want my tau net to equal 0, or this whole thing is not rotating, that better be true no matter where I pick that pivot point, right? If I pick my pivot point to be this far left end of the bar, my torques calculated for all these forces based on this pivot point better be 0, because the bar is not rotating with respect to this point. Let's say I pick my pivot point to be where the tension is. It still better be 0, because the bar is also not rotating around there. Same thing if I picked it here. Bar is also not rotating around FA, the point where Anthony is pushing, so that better be 0. And the same is true if I picked any point in space. These might not be particularly useful and will be hard to solve the problem with, just a lot of geometry and extra calculations, but tau net will still come out to 0 because this bar is not rotating around any point. So based on the fact that we have the freedom to choose any point as our pivot, which one makes the most sense for this problem? Which one will be the easiest to calculate? Well, let's look at the information that we already have. We know the weight of the bar. So we're told the bar weighs 20 kilograms, the bar's mass. So Fg for the bar is very easy to calculate, right? It's just its mass times gravity. So what else? We're told the force from Anthony. We're just told Fa is 325 newtons. Great. We're trying to find Chelsea's mass, right? So that's this Fc is going to be important. We need to know what her mass is to know what type of force she pushes on the bar. But we're not told anything about this tension force right here, this T, the force that the rope is pulling up on the bar. And so it would be really nice if that doesn't factor into our equation. Otherwise, it's just going to be an unknown. So how do we get this tension to not factor into our equation? Well, what if we just put that tension force, or the pivot point, right where the tension force acts? If I put my pivot point here, the R for this force is 0. So it doesn't produce any torque, right? We can't produce a torque by applying a force to the pivot point itself. So that leaves our entire torque balancing equation to only use forces that we either know or want to know something about. So that's great. So why don't we go ahead and write our torque balancing equation then? So since tau net is 0, that means our total tau into the page is going to equal our total tau out of the page, right? So let's identify, based on this pivot point, which taus go in and which taus go out. So here's our pivot. Fg and Fc are both pointing down, and around this pivot point would make this bar rotate clockwise, right? Like this. So if we use our right-hand rule, which you should check for yourself, if I curl my fingers in that direction, then my thumb is pointing into the page. So both of these forces are torques into the page. And then Fa is pointing up. That would make this bar want to rotate from our perspective counterclockwise, which is, using the right-hand rule, out of the page. So now, going back to our torque balancing equation, the sum of the torques into the page is just going to be the torque from the gravitational force plus the torque from Chelsea's force, and that's equal to the torque from Anthony's force. So here's our torque balancing equation. We can go one step further and see what these torques are made up of. Torque from gravity is just the force of gravity times its radius, right? So this would be Fg Rg. Same thing for the others. Tau c will be Fc Rc, and tau a will be Fa Ra. Now, Fg is just the mass of the plank times g, 10 meters per second squared. So this, we know that's 20 kilograms times 10 meters per second squared. Fc is unknown. That's the force that Chelsea applies on the bar, which is based on Chelsea's mass. We don't know that yet. So we could just write mc times 10 meters per second squared, right? This is mg, and we just don't know m, times rc, which we do know. And actually, whoops, I forgot rc. So Fg, we know, is the force of gravity. That is mg. So this term is from the mass of the bar. So m is 20 kilograms. We know that's the mass of the bar, 20 kilograms times g, which is 10 meters per second squared, times rg, which is the distance that force is applied from the pivot point. So if Fg, we said, acts at the center of mass, that means that it is 0.5 meters from the left edge of this bar, right? From, use a different color, from here to here is 0.5. And so if our pivot point where the tension is acting, we're told is 0.2. So if this is 0.2 meters, then this distance from the tension to the force of gravity must be 0.3 meters. So Rg, well, let me go back to blue. RG is 0.3 meters. Okay, plus FC. We're not sure what the mass of Chelsea is yet, but that's going to be her mass times gravity. So why don't we just leave that as FC for right now? And we know that her distance from the point where the tension applied, well, tension is 0.2 away from the left. Chelsea is 0.6 away, so the difference is just 0.4 meters. That is the radius of her, or the position vector for her force, the distance from the pivot point. Then for Anthony, he is applying this force way at the other end. So if he's all the way at 1 meter away from the left side, that's the length of the bar, and it's 0.2 from the left to the tension, then he will be a distance of 0.8 meters, and we're told that his force is 325 newtons times 0.8 meters. Okay, so now we have an equation where the only unknown is the force from Chelsea. So we can move this 325 times 0.8, or why don't we do the other thing, because FC is already on this side. Let's move this expression, 20 times 10 times 0.3 over here, subtract that off, and then if we divide by 0.4, we'll find that FC is equal to 325 newtons times 0.8 meters minus this piece, 20 kilograms times 10 meters per second squared times 0.3 meters divided by 0.4 meters. This whole thing divided by 0.4 meters. And if we plug that into our calculators, we should find that's equal to 500 newtons. Okay? And now, we don't want just the force that Chelsea applies. We're almost there, but we know that FC is equal to MC, her mass, times G. So 500 newtons is equal to her mass, the thing we want to find, times 10 meters per second squared. And if we divide by 10 meters per second squared on both sides, we find that MC is equal to 50 kilograms. And there's our answer. So from this, we actually only needed to use the torque balancing equation because we kind of did the clever thing and picked our pivot point to be where the tension's applied, so that tension doesn't come into the equation at all, and we never have to deal with it, at least for this piece of the problem. However, we could still solve this if we picked another point along this plank, or in fact anywhere in space, but it probably makes sense to at least put it on the plank. If we put it anywhere there, we would still be able to find the same thing, except we would have two unknowns. In that case, we would have the mass of Chelsea, or the force from her, and the force from the tension force. And in that case, we would have two unknowns, one equation, and the second equation that we would need to solve that is this F net equals 0. So we would have to do the force balancing, and we'd get another equation that involves both tension and the force from Chelsea, and we could use those two equations, two unknowns, to solve. You can go through that if you'd like, just as an exercise, but it is a little more tedious. But we'll go ahead and do the force balancing anyway for this next problem. So we're asked to calculate the tension in the rope. So we know that when we did torque balancing, at least with this as our pivot point, we didn't need to factor in tension at all. But like I said, we still have this F net equals 0 equation that we know is true because we're in static equilibrium. So let's try to use that. If F net equals 0, that's true for both the x and the y components, right? F net x equals 0 and F net y equals 0. However, none of these forces have an x component, right? So F net x is obviously 0 because that's just 0 plus 0, whatever. None of these have an x component. And actually, that's the piece that I didn't even explicitly mention before. Because none of these have an x component, and their distances from the pivot point are all horizontal, we didn't have to fiddle around with trig and figure out what F perpendicular or R perpendicular or anything like that is for this problem, because they're already perpendicular, right? My vector from my pivot to FG, from my pivot to FC, from my pivot to FA, all of these are already perpendicular to all the forces. So that's why I could just multiply force times R, and not have to do any component breakdown. So anyway, similar simplification for here, F net Y, they're already all in the Y direction. So we don't need to do any trig, and the Y components are just equal to their entire magnitude. So in the Y direction, my total force, let me switch back to blue, my total force is just tension plus Fg plus Fc plus Fa. Right? All these forces are all in the Y direction, so they have to add to 0. We know that Fg and Fc are negative, right? Because they're pointing down, and these two Fa and T, or tension, are positive. So you have two forces going up, two forces going down. They all cancel. So if we wanted to make a free body diagram, which we don't have to for this problem, but might as well, again, we collapse. For a free body diagram, we just collapse the object to a point and put all the forces on top of that point. So we'd have our tension going up, our Fa going up, and then the other two, Fg and Fc, all pointing down. I kind of extended it a little bit by already adding the vectors, so I already put them tip to tail, but that's just so it's easier to see that the up pieces cancel the down pieces. We could also just draw them all right on top of each other, but that gets a little messy. Anyway, this equation lets us see that, lets us see exactly what this picture shows. So let's go ahead and solve it for the thing we want, which is T. So T, the tension, let me go back to blue, T, if we just move everything over to the other side, is equal to minus Fg minus Fc minus Fa. And the way we've done this here, we know that Fg and Fc should be negative. So what are those here? So we have negative, negative, so these terms are both going to come out to be positive. Fg, like we said before, is just this 20 kilograms times 10 meters per second squared, so that we can move that here, 20 kg times 10 meters per second squared. And again, like we have a double negative here because we said Fg is negative and we have minus Fg, so that's going to be a positive term. Same thing for Fc, double negative, Fc is pointing down and we have minus that, so we get plus. Fc, we could either do mc times g, but we also already just calculated Fc is 500 newtons. And then Fa, we have, that is minus because we have minus Fa, and Fa is positive, and we calculated, or Fa here is 325 newtons. No calculation necessary. We are just given that in the problem statement. And the result of this, we get 200 plus 500 minus 375, we get 375 newtons is our tension force. This is a question that's often asked, like calculate the tension in the rope, or what is the tension, something like that. Tension is just a force. It's a specific type of force when a rope or a chain or something is applying a force to something, like pulling on it. But tension is just a type of force, which is why the units are newtons. And we don't have any like positive or negative sign here just because it wants the tension, or like the magnitude, I guess, is the way to think of it. But we know this tensional force is applied upward at the point that we see in our free body diagram. Okay, so now we use torque balancing to find Chelsea's mass. We use force balancing to find the tension. Now the last piece, Anthony is getting tired. Should Chelsea move to the right or to the left to make it easier for Anthony to hold up the bar? And of course it wants us to explain. So let's redraw our picture real quick just for explanation's sake. So we have our tension force, gravity, Chelsea, Anthony here. And we want to reduce the force that Anthony has to apply. So we want to make it easier for him by changing the force that Chelsea applies. And so why don't we try our force balancing equation first? So our force balancing equation, we found that tau plus Fa equals negative Fg plus Fc, right? That's just rearranging this equation here, bringing these two to the other side. And this is just saying that the forces in the positive direction, on the positive y direction, are up forces equal equal and opposite to our forces that point down, right? And so if we want to decrease the magnitude of the force that Anthony has to apply, we want to decrease the force that Chelsea has to apply, or that Chelsea is applying, right? But we can't do that because Chelsea moving to the right or the left does not affect her force, right? So that actually doesn't work. How can we reduce the force that Anthony applies? Both of these, both Chelsea and gravity, because Chelsea's force is a gravitational force, both of these don't depend on position at all. Her moving to the right or left obviously won't change the weight of the bar. It won't change her own weight, so it won't change those forces. So the only thing we're left with being able to change is this tension force, right? So if Fa goes down, to keep this equation the same, tension must go up. But that doesn't really give us an answer to our problem, because we know how we would want to change the tension. So what this shows us, if we want to make it easier for Anthony, we want to increase the tension in this rope on the left, and that will lighten his load. But how do we do that? By making Chelsea move. So for that, we'll have to look at our torque balancing equation. So our torque balancing equation shows, let me go back to blue or black. Fg Rg plus Fc Rc equals Fa Ra, right? This is tau G, tau C, and tau A. All of the torques into the page on the left, torque out of the page on the right, and they have to be equal in magnitude. So again, we want the force of Anthony to go down. We want to make this easier for him. And so how do we do that? Well, Fg and Rg don't change, right? This is the weight of the bar. This is its center of mass. Those are the same. Fc also doesn't change, like we just said. Her mass doesn't change. However, we can change R. That's what moving to the right or left is. It's Chelsea changing the distance away she is from our pivot point, which is we're considering to be the point where the tension acts. So if we want to decrease Fa, we also have to decrease her distance from that pivot point. And how do we decrease it? Well, this is the distance that she is from it. So if we want to decrease it, she'll have to move to the left, right? So that's how we find that she must move left in order to reduce her torque into the page, which lessens the amount of torque that Anthony must provide out of the page. And since his R isn't changing, that just decreases the amount of force he must apply. And what that tells us is that when Chelsea moves to the left and reduces the amount of torque that she provides, that's actually going to increase the tension in the rope. The question doesn't ask about that. We're not concerned with it at all, but it has to be the case, right? Based on this example right here, I mean, this force balancing equation is still true, right? If Fa goes down, tension goes up. And we know that Fa does go down. When Chelsea moves to the left, R decreases, and so Fa must decrease since none of the other things are changing. And if Fa decreases, tension goes up. So that's just a side effect of Chelsea moving to the left. I guess intuitively what we can think of that meaning is there's also gravity, but gravity's not changing here, so we can kind of ignore it for now. But the two sides of this plank are supported by two different things. On the left, it's supported by the tension in the rope. On the right, it's supported by Anthony. So whichever side Chelsea is closer to will feel more of her mass. So that's almost like a seesaw, right? If you move to the left of the pivot point on the seesaw, the left side tilts down, it feels that mass. If you move to the right side tilts down and feels more of it. So a similar thing's happening here. There's no motion, but the amount of force changes. When Chelsea moves closer to the tension has to increase to make up for it. And when Chelsea moves closer to Anthony, his force upward has to increase because of it. So that's the way to think about it in the context of forces.